Hi everyone. Now I'm going to start a new chapter of the book that I'm following. It's called Applications of Differentiation. Okay. So, for example, when you see a graph like this, right? Look at this. So, I'm going to try to get a darker color here. So we got a minimum here, okay? But how can we find, this is the function x squared plus 1 in the interval from -1 to 2, okay? So it goes this way, right? Now, how do we find out what the minimum point is? Because these minimum points where the tangent is 0 or where the tangent doesn't exist, these are called critical points, okay? That something is happening in the graph in these points. So for example, how do we find out what the minimum is here? Well, you can see that the tangent here is going to be negative, and it's becoming less negative, less negative, less negative, less negative, and then it becomes 0 here, right? It becomes 0, it becomes a horizontal line, and then it starts becoming more positive, more, and if it keeps going this way, I think it'll reach infinity, like, right, it'll be kind of like that. Almost a vertical line. It'll be something like this, kind of like that. You know, it's not a vertical line, but it's almost a vertical line. Okay, so how do we find this stuff? Well, in this case here, it's easy, right? The tangent, the formula for the tangent of a graph is the differentiation of that graph. It's the first derivative of that graph. So in this case here, you have, I'm going to change the color here. In this case, you have x squared plus 1. So the derivative of the function here is just going to be 2x, right? Now you got to find out when this is 0. Well, it's going to be 0 when x is 0. So when x is 0, we know that the tangent is going to be 0, okay? Now, putting this in the formula of the graph, you got x squared plus 1. So when x is 0, you got 0 squared, which is 0 plus 1, so it's 1. So we know that the point, if you're going to put a little table here, like 0 and 1, this is a critical point, and you got it right here, okay? I'm going to change the color again. You got this point right here, 0 and 1. That's where the tangent. So why is this a critical point? Well, you can say that the tangent in here was negative, okay? And then over here it became positive. So you can say that it's a critical point, okay? You got an interval at this point from, I don't know, maybe x less than or equal to 0 and greater than -1, yeah. Okay, greater than or equal. I'm gonna put this like that because it's a closed interval, right? It's from -1 to 2, and -1 and 2 are part of this graph. So you can say that it's you can say that for this interval right here, okay, when x is greater than or equal than -1 and less than or equal to 0, you're going to have a negative tangent, and when x is 0, it's actually going to become, well, I'll tell you what I'm going to do. I'm going to do this. So x is greater than or equal to -1 and less than 0. The tangent here is going to be negative, okay, so the slope is negative. For x equals 0, the slope is 0. And for x greater than 0, okay, and x greater than 0, and x is less than or equal, you can put it like this, less than or equal to 2, okay. An x in here. So x is less than or equal to 2 and it's greater than 0. The slope in here is going to be positive. Okay, so that's a critical point. The 0 and 1 is a critical point, and you can see that the 0 and 1 here by inspection is a minimum, right? Because you got a negative slope and then a slope of 0 and then a positive slope. So you got a negative slope like this, and then the slope becomes 0 at this point, and then it starts becoming a positive. So you know that at least in this interval from here all the way to here, this is a regional minimum, okay? It may not be a global minimum. Maybe the graph is going to do something like that, and you're going to have an even lower minimum in here, or maybe not. For example, in the case of a parabola, right, you got something like that. So this is going to be the global minimum, or it could be the global maximum if you have a positive slope, and then you got a negative slope, a 0 slope, and then a negative slope, and becomes more and more negative. So you know that this is a global maximum, or you could have a regional maximum like this. Okay. So from this point here, well, yeah, you can say from this point all the way to this point here, you got a regional maximum here. But then from this point on here, you got another regional maximum here, which could be a global maximum, or maybe not. Maybe there's going to be an even larger maximum later, which is here, okay? So that's the concept here. Let me think here. Well, let me get this. I'm going to show you something. The book is saying that a minimum can exist even though the limit doesn't exist. Why? Because coming over here this way, what do you have? You have, this is the absolute value function. So the minimum over here, well, not the slope over here from, in the interval, let me get the interval. X is less than 0. The slope in here is -1, okay? For x greater than 0, the slope is 1, because that's the value of the tangent, right? So since you got for x coming from the let me see, as x approaches 0 from the right, you got a positive slope, and x approaching 0 from the left, you got a negative slope. So the slope, the limit at 0 doesn't really exist, because this function is continuous at 0, okay? I mean, it's defined, but it's not continuous, okay? Because you got a tangent here, and then abruptly at 0, it changes. And if you're gonna start from 0, you go to the right, you're gonna have a positive slope. If you start from 0 and go to the left, you're gonna have a negative slope. So this is not a continuous graph, okay? The tangent doesn't gradually change. You got something negative here, and you got something positive here. What about here? What's the slope gonna be? Well, it depends. If you go from this point, from the 0 to the positive side, you're gonna have to the right side, you're gonna have a positive slope. From this point to the negative side, to the left side, you're gonna have a negative slope. So the slope just doesn't exist, not continuous, okay, at 0. When it gets to the 0 point, x equals 0, you don't have a slope there. What's the slope of x equals 0? You don't have it. It depends. You got a slope on one side, and you got another slope on another side. So in one point, you have two slopes completely different, and they're changing abruptly, okay? You don't have a gradual change like this. It's not like that, okay? You got a gradual change. No, you got, it's like a lightning bolt. It just changes. So in this case, the limit doesn't exist, but the minimum exists. So you don't actually have to find, what I'm trying to say is that in order to find the limit of a function, you don't actually have to find the first derivative of that function and make it 0. Maybe the first derivative doesn't exist. In this case, it doesn't exist. Okay, at x equals 0, the first derivative of the function does not exist. Okay, so that's a minimum too. So let me show you guys something here. This is another thing here, okay? Now look at that, the function is sine of x. So the first derivative is going to be cosine of x. And what do you want? You want to find out the critical point. So the cosine of x, when is it going to be 0? Well, the cosine of x is going to be 0 at n pi divided by 2, where n is an integer, okay? I don't know if it belongs to the integer like that. I don't know if it's if this is the symbol like that. I don't know. I forgot the symbol for the integer numbers, for the integer set of numbers. So, for example, here, what do you have in here? Look at the graph. When pi is divided by 2, you got a relative maximum here. Why is it relative? Because it's gonna be from this point here, okay, this point here, all the way to this point, kinda here. In here, you're gonna have another maximum because the graph is just gonna keep coming like that, okay? So in this point, you got another maximum. So you got a relative maximum and you got a relative minimum, okay, on this point here. And you can see that in the relative minimum, let me think here just one second. If it's 2, it's pi, right? Now n cannot belong to the integer. N is not an integer. N's gotta be, well, it's gotta be an integer. Hold on. It has to be an integer, but it has to be like an odd number. Okay, because if it's an even number, if n is 2, it's going to be 2 pi divided by 2, which is pi. What's the cosine of pi? Is minus 1. Okay, and we want when the cosine of this is going to be 0. So it's got to be x. This x right here has to be n pi divided by 2, where n is an integer and n is an odd number. So it can be pi divided by 2, 3 pi divided by 2, 5 pi divided by 2, 7 pi divided by 2, and it just keeps going, okay? So, yeah. I don't know if there's a formula here that I can think of. 2n, maybe 2n plus 1. When n is equal 0, then... Or maybe I can put a 2n plus 1. When n is equal 0 is going to be 1. When n is equal 2 is going to be 5. No, forget it. Okay, so that's why n's got to be part of the integer and it has to be an odd number. Okay, and it just keeps going the other way too. If you go minus pi divided by 2, minus 3 pi divided by 2, minus 5 pi divided by 2. In all of these, the cosine of x is going to be 0. So these are all critical points, as you can see in the graph here. Okay. Let's say you have a function three x to the fourth minus 4x cubed. Okay. Well, the domain is closed one, so x is greater than or equal to minus 1, and it's less than 2, less than or equal to 2. Okay. And he wants to find all the extremes, all the critical points in this part. Well, let's find the first derivative. The first derivative is going to be 2x cubed minus 12x squared. So you want to know when this is 0, okay? Critical points is when we have this equal to 0. So let me do this. Okay. Now, let's just factor out the x squared. So you got x squared and have 12x. Well, you can do 12x actually. Yeah. 12x squared, so it's going to be x in here. And here you can do minus 1 is equal to 0. Okay. Now you can just get this part here and pass it dividing, which is just going to be 0. So yeah, you have two things in here. When 12x squared equals 0 and when x minus 1 equals 0. So from here, you can see that this is going to be when x equals 0 and when x equals 1, okay? So at these 2 points, you're going to have critical points. So what are the intervals here? It's going to be from minus 1 all the way to 0. Yeah, all the way to 0. Let's see here. Let me think. All the way to 0, but it's an open interval because at x equals 0, the slope is going to be 0, and at x equals 1, the slope is also going to be 0. Okay, so in here you're going to have a slope. So you got an interval here. Now the next interval is from 0 all the way to 1. Okay, and the next interval is from 1 all the way to 2. Okay, now, yeah. So what I'm doing is breaking this interval right here into 3. Okay. And if you just put that stuff in there, for example, let's just say this. From minus 1 and 0, okay, so the slope is going to be 1. So let's put minus 1 because it's a closed interval, so minus 1 is part of the function, it's part of the domain. So let's just replace minus 1 into here so we can find out the slope. Okay, minus 1 is going to make this minus 12. Okay, I'm going to put this stuff in here, guys, and this is just a sketch. Okay, so something to write. Minus 1 cubed minus 1 times 12 minus 12. And then you have minus. Now what do you have here? Minus 1 squared, 1 times 12, 12. But you got a minus, so you got a minus 12 here. So this is minus 24. It's a negative number. So you know that the slope in here is going to be negative. Okay, I'm going to put slope. I'm going to represent slope with an m. Okay, I'm going to say that m is less than 0. It's negative. Okay. In this interval right here, from 0 all the way to 1, but in an open interval, that means that 0 is not part of it and 1 is not part of it. Let's put half, okay? So, if it's half, well, it's going to be half cubed. It's going to be 12 divided by 8 in here, minus, it's half, right? So, it's going to be 1/4, 12 divided by 4 is 3. Now you want to get this 3 out and you want to put an 8 here. So you already put the 8 there. Times 3, 24. Okay, so this is going to be minus 12 over 8. So it's also negative. So you know that the slope in here is negative 2. Let me erase this. The slope here in this interval is going to be negative. Now let's see 2, this interval here, okay? So we're going to replace in this formula again. It's going to be 8 times 12 is 96 minus 4 times 12 is 48, okay? So we know that this is going to equals 48, which is positive. So here, the slope is positive. So you see, what you're going to have is something like this. Something that comes negative, and then you have this. And then it starts being negative again until it gets to 1. Okay? And when it gets to 1, it becomes positive. It's something like that. This is just a messy sketch. Now, take a look at this graph, this mess that I made in here. Okay, and I'm going to show you guys the real graph. There you go, look at that. They kind of look, you know. You got a negative part here. you got a negative part here, and then it becomes 0, and then it starts going down again because the slope is also negative. And then at 1, the slope is 0, and then it becomes positive, okay? So you know that at least in this interval from -1 to 2 inclusive, you have two critical points, one at x equals 0 and another one at x equals 1, okay? And if you want to find out, okay, so how do you know that when x is 0, the y is going to be 0? All you got to do is to replace it in this formula here. This is the formula of the graph. Okay, so when you put a 0 here, it's pretty obvious that you're going to have a 0 there. And when you put a 1, well, it's just going to be 3 minus 1 cubed, 1 times 4, 4 with a minus, minus 4. So you go -1. So you can see here that you got the point. Let me see again. You got the point 1 and -1 here. Okay. Yeah, now I'm going to show you guys something. Let's go back to the quadratic equation, the one that draws a parabola, okay? Parabola is something like this or something like this. Concavity up or down. Now what's the formula, the general formula of this parabola? F of x equals, you got ax squared plus bx plus c. This is the general formula of the parabola, okay? Now, what do we want? We want to find the critical point, because you know that the parabola is just going to have one critical point. It has a minimum here, or it has a maximum here, okay? In here, a is greater than 0. In here, a is less than 0. A cannot be 0. If a is 0, then this function, this term in here becomes a 0, and you don't have a quadratic equation anymore. Now you got a linear equation, which is bx plus c, which is a line, okay? A straight line. So let's see here. We got to find the critical points. Well, what do? We got to make this f of x equals 0, the first derivative equals 0. Now, what is the first derivative? Well, let's differentiate f of x with respect to x. You're going to have 2ax plus b, right? C is the constant term, is just going to be 0. So this has to be 0. So what is the x for this? Well, you see that x, 2ax equals minus b, x equals minus b divided by 2a, okay? So whenever you have a quadratic equation and you equate x equals minus b divided by 2a, you're going to find the x that has the minimum. Now, a lot of people are thinking, okay, what if I want to find the y that has the minimum? All you got to do is to apply this x in here. But let's do that in the general formula to see what we come up with. So if you plug this x in here and in here, you're going to come up with a y, because this is y, okay, this is y. You're going to come up with a y that is the y coordinate for the maximum or the minimum of the parabola. So let's just replace it in there. You got a times this squared. So, okay, so it's going to be b squared, okay, divided by 4a squared. And then you have plus plus b times minus b, so it's going to be a minus. So you have a minus b squared divided by 2a plus c. This is the y critical. Let's just put the yc, the y critical. All right. Now, what do we do here? What we can do is, let's unite all of these. If I want to unite all of these, what I gotta do is to use the minimum the minimum common denominator, right? Which in this case is going to be 4a squared. Now 4a squared divided by 4a squared, 1 times ab squared, okay? Minus 4a, it's a lot easier if I do it another way, but that's fine. 4a squared divided by 2a is 2a times b, so you got 2ab squared. And in here, you're going to have 4a squared c. Okay. All right. Okay, yeah. This equals the y critical. Now you see that you have a everywhere. So let's get some of these a's out. Okay, you're going to divide 4a squared by a, which is just going to be 4a. This a in here, ab squared divided by a, b squared. Minus 2ab squared divided by a, this, you make this a disappear. 4a squared c divided by a, 4ac. All right. Now, something else that we can do. Let me think here. Okay. Well, let's see here. What do we have here now? I was just thinking about something else. Sometimes I zone out. Okay, so b squared minus 2b squared is going to be minus b squared plus 4ac divided by 4a. This equals the y critical. Okay. Now, guys, you know what we can do? We can do this. Let's extract the minus from the numerator. So we're going to do minus b squared. Where am I going with this? Well, if you're going to extract the minus from the numerator, you factor out the minus. So you got a minus here. So minus b squared divided by minus b squared plus 4ac divided by minus 4ac divided by 4a. This equals the y critical. Okay. Now you guys recognize this? This is the delta of Bhaskara's formula. I don't know if it's pronounced this way, Bhaskara, okay? But it's that guy, I think it's Bhaskara. Maybe it's like this, Bhaskara. Or maybe the A, Bas, and you got a K here, Bhaskara. Yeah, it's some of this stuff. This is Bhaskara's formula. So what is the y? This is the x critical, and what is the y critical? The y critical is going to be minus delta over 4a. That's it. So that's where these formulas come. Okay, when somebody gives you something, for example, let's say that this is 3, b is minus 2, and c is 5. And somebody tells you, okay, I want you to find the x critical and the y critical, which is the point of either minimum or maximum. Since the 3 here is positive, I know it's going to be a minimum here. All right. So that's what you do. You do minus b divided by 2a to find x, and to find y is minus delta over 4a. And that's it for now. Let me see if I want to continue with this video. Okay. So let's have here function equals x squared minus 3x plus 2. Okay. Find the y critical and the x critical. Well, the x critical equals minus b over 2a, and the y critical equals minus delta over 4a. So minus b over 2a, it's going to be 3 divided by 2. So I know that this, why? Because minus b. So you got a minus, and here you have a b, which is minus 3. So minus 3 divided by 2 times 1, because a is 1 here, which is 2, okay? So this equals that. It's because sometimes I do things very fast, because I don't want to bore everybody to death. So x critical equals 3 divided by 2. The y critical is going to be b squared, which is 9, minus 4a. 4 times 2 is equal to 8, so it's 1. Okay, so 1 is the delta. So it's going to be minus delta over 4. And there you go. That's the x critical, that's the y critical. What is this? The x critical is when you have this. What is the coordinate of x in here? It's gonna be 1/2. And what's the coordinate of the y here? Is gonna be negative 1/4. So here you can get some assumptions here. Let me just show you something. All right. We know that this thing here, the x is 1/2. So if you have 1 here, and 2, and 3, and 4, and 5, so you know it's going to be here at this point, okay? But the y critical is negative. So if you have 1 here, you got 1/2, and 1/4 is half of the half. So the minimum is going to be kind of like here, okay? And you know this thing is going to come this way, and it'll come this way here. How do I know the concavity is up? Because a here is positive, a is 1, and that's it. Maybe another exercise. Okay. It's asking to find x to the 4th minus 2x squared. It's asking to find the critical points in this interval. I'm going to put a domain here. This D is looking like a P. Okay. The domain equals minus 2 and 2. I like to put a semicolon instead of a colon because in some countries the decimal is a comma. I like to put a semicolon instead of a comma. Okay. Some countries you write, for example, minus 2.1. Well, in Latin American countries you write minus 2, 1. Not 2 point, point they use to separate the thousands. For in the United States, if you want to write 1500, you write it like this. And if you want to write 1.500, you write it like that. In Latin America, it's the opposite. 1,500 is 1.1500. It's crazy. And 1.500 to them is 1500. Okay, it's 1,500. So they're the opposite. I think it's whack. I don't know why they do this, just to complicate things. So I like to put a semicolon here because then I know that I'm separating the numbers. Okay. All right, so let's find this. Well, the first derivative equals 4x cubed minus 4x. And you want this to be 0, so I'm just going to put it over here. Let's equate this to 0. No. I actually have to make an equal here. So I want this. I gotta keep it organized, guys. I just can't do it. Okay, I gotta make this equal 0. So you can factor out the 4x, and you got x squared minus 1 equals 0, which means x equals 0 or x equals 1. Well, x equals plus minus 1. Okay, why? Because you see, if you pass the stuff in here dividing, 0 divided by this is 0. 4 and then 4x equals 0, x has to be equal to 0. If you pass this stuff in here dividing, right, what you're going to have is x squared minus 1 equals 0, x squared equals 1, x equals, and then you got a plus or minus 1, which equals plus or minus 1. Why? Because minus 1 squared equals 1, okay? And 1 squared also equals 1. So, yeah. So you have these three critical points, okay? Since the domain is from minus 2 to 2, you know there are going to be some intervals here, okay? So it's going to be from minus 2 all the way to minus 1, open, because when it's minus 1, we know that the slope is going to be 0, okay? And then you got another domain from minus 1 all the way to 0. You got another domain from 0 all the way to 1, and then you got another domain from 1 all the way to 2. Why just 2? Why not infinity here and negative infinity here? Well, because of this domain, the exercise is asking us just to consider this from minus 2 to 2, excluding the minus 2 and 2. For you guys that don't know this notation, when you do this, minus 2 and 2, that means that the minus 2 and the 2 are part of the graph. When you do this, minus 2 and 2, it means that the minus 2 is not part of the graph. Anything to the right of the minus 2 is part. So minus 1 point, that's part of the graph, but minus 2 is not, okay? And 2 is also not part of the graph. So everything up to 1.999999999 is going to be part of the graph, but 2 is not going to be part of the graph. It's not part of the domain, okay? So there you go. So you have all these things. If you want to find out what the slopes are going to be, all you got to do is to replace something in the middle. For example, in here, minus 1.5, which is between minus 2 and minus 1. You plug this in here and see what the outcome will be, and then here you can use a minus half, and you plug that in there too and see what it will be. In here you can put a half, okay? In here you can put a 1.5. I like these half things. It doesn't have to be half. For example, it can be 1.00000001. That's valid. That's between 1 and 2, okay? But I'm just trying to so you're going to have all these mini domains in here in the function. And between the domains, for example, in here, the slope will be 0. So m is 0 here, m is 0 here, and m is 0 here. Let's see. I'm going to show you guys the function already from the book. There you go. Yeah, I'll put it here. Let me see. Yeah, put it like that. Okay, so let's see here. So you guys can see that between minus 2, okay, here you got a minus 2, and here you got a minus 1, the x value, right? And what do you have? You have a negative slope in here. So this slope is negative. Slope is negative here, and then the slope becomes positive, so the slope in here is positive. The slope in here is going to be negative, okay? So the slope is positive from minus 1 all the way to 0, excluding these points. From 0 to 1, excluding the points, is going to be negative, and from 1 to 2, it's going to be positive. So there you go. You found all three critical points between minus 2 and 2, excluding the minus 2 and the 2, right? This is wrong because the exercise over there says that it's excluding, but you got a closed. It's not a closed. It's a full circle here, a full dot, and you got a full dot in here. These dots should be open. Okay, they should be like this. They should be like that. Like this. They're not supposed to be filled, because if it's filled, it's a closed interval, but if it's open, if it's not filled, it's an open interval. Okay, and when you have D equals open interval minus 2 and 2. That means it's supposed to be like that. It's supposed to be open, empty circles, empty dots in here and in here. Okay. Let me see if I go to the next one here. Or maybe I'm just going to end this video now. Yeah, now I want to talk to you guys about something called the mean value theorem. The mean value theorem states, okay, let's just say that you got a graph like that. I'm gonna do something like this. Okay, and it starts in here and it ends in here. Let's find the secant, okay, which is just this value of y minus this value of y divided by this value of x divided by this value of x. That's going to be the average, right? It's the secant. When we started this calculus course, I told you guys the difference between secant and tangent. The tangent just touches one point of the graph like this, right? And these are the tangents, and the secant touches 2 points of the graph. You can see that this is a secant. All right. What does the mean value theorem state? It states that at some point in here, I don't know, some point in this graph, there's gotta be a tangent that has the value of this secant, which makes sense, okay? Because in here, this is not supposed to go down. I know it kind of looks down here, but it's because I'm not a robot. So in here you gotta see, okay, let me try to fix this. It's actually going this way. Now I'm gonna have to draw in here. This is supposed to, this is never going down, okay? It's always going up. It starts at 0 and starts going up. Okay. So you can see that if you have a tangent here, it's kind of 0, right? At this point. And then as it comes over, the tangent's going up. If I bring it over here, the tangent is a little bit more up. And if I keep bringing it kind of here, the tangent's gonna just keep increasing. And at some point, for example, in this case, it's gonna be this one where the tangent is actually parallel over here. You see that? Let me make it parallel. So at some point in here, which visually we can see that it's this point, the tangent has to be parallel to the secant. That's what the mean value theorem states. Okay, if you have a secant, so in a domain from here all the way to here, okay, in this space here, in this space, so going from the left all the way to the right, you can draw a secant, okay, which is the final point minus the initial point. Okay, great. And this secant is going to have a tangent. It has a tangent of its own. The tangent of the secant is this one in here. It's the secant itself, okay? This is the tangent of the secant. It's continuous. Now, along the graph, you're going to have many secants. A secant here, a secant here, a secant here, a secant, secant. Okay? Oh, not secants, tangents, mini tangents. Mini tangents, tangents. One of these tangents has to be equal to this. All right, that's what the mean value, yeah, one of the tangents has to have the same tangent as the tangent of the secant in that domain. That's what the mean value theorem states. Of course, these are not the actual words, but that's how it's interpreted, right? Now let's see here. Let's say you have a graph function of x which equals 5 minus 4 divided by x, okay? The open interval is from 1 all the way to 4. Of course, 1 is excluded from the graph, from the domain, and 4 is also excluded. Okay, now what is the tangent of the secant? Well, the tangent of the secant is going to be f of 4 minus f of 1 divided by 4 minus 1. This is going to be the tangent. Okay, I can't say that this is the derivative. I'm just going to say that this is the, I don't know what notation I should use here. I'm going to say that this is the tangent of the secant. I'm going to put m, and then I'm going to put a little s in here that says the secant. Now, what is f of 4? Well, putting a 4 here is going to be 5 minus 1, 4. So this is going to be a 4. Okay, plug in this 4 in here and find the value of y. So 5 minus 1, 4, minus, when this is 1, is going to be 1 here, divided by 4 minus 1. So this is 1. Okay, so this equals to 1. All right, that means that there's got to be a c. What does the mean value theorem state? There's got to be a c for which the tangent of the derivative of the function at point c equals 1. That's what the mean value theorem states. Okay, if you differentiate this function in here and then you plug in, you make this becomes 1, you have to find a c for it, and this c, this 1 point, has to be between 1 and 4. So let's see. Okay, this is something that has to happen. Okay, so let's differentiate this. Differentiating f of x, you're gonna have a 0 and you got a minus. So what is this? This is 4 times x to the minus 1. So putting the minus 1 over here and multiplying x to the minus 2, this is the derivative. Okay, you can do this a little bit slower later, but the derivative is just going to be 4 divided by x squared. Okay, now 4 divided by x squared, you have to have a 1. You want this to become a 1. Why? So you can find the x, which is the c that's between 1 and 4, for which the derivative is 1. Okay, so cross multiplying this, you got x squared equals 4, x equals plus or minus 2. We're just worried about this interval here from 1 to 4, so the minus 2 is out. Okay, so you got a 2. So 2 is exactly this c, okay, that when you plug in into the derivative of the function, or the differentiated form of the function, you're going to have a thing of 1. You're going to have a tangent of 1. So when x equals 2, the tangent, I'm just going to put a 2 here, is going to be 1. 1 is the same tangent that we found here of the secant. Remember, it's the same tangent of the secant. This equals the tangent of the secant. And guess what? This 2 here is in this interval. And is between that interval. That's exactly what we said. I want to just show you guys something here. Why is it obvious? Okay, if you have a function like that. Now let's just say that, so the secant, let me do this here again. So this is the secant. Okay, you gotta have a tangent with this value. You're gonna say like, oh no, you don't have to have a tangent with this value. Are you sure about that? Let's just say that you got a tangent here, and then you got a tangent that keeps going this way. What is going to be the graph? The graph is going to be kind of like that, okay? This is going to be the graph, kind of like this. It's not going to be a graph like this one. Can you see the cross? I don't know if this is called a crosshair or whatever. The mouse thing. this is the graph, okay? So let's just say that we got another tangent now. The tangent goes like this, these mini tangents, right? And they keep going, and they keep going, and they keep going. And before they reach this inclination, they're already going down. And now you got another one like this, and they start going up again, but they already go down. And they start going up again, but then they already go down, okay? They never reach this inclination. If they're not going to reach this inclination, you know what the tangent, what the secant is going to be like? The secant will be this. It's not going to be this one here that's shown. So it's obvious, okay? If you want the graph to go from down here all the way up there, at some point the tangent has to be equal to this, okay? You start in here, no, 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 you start. When it gets to this point here, look at that. The inclination is the same one as this one here. So, and this point here is between these points, is between the extremes, right? You got an x here, you got another x here. This point here is between it. So it's kind of obvious when you think about it. But of course, in mathematics, we got to prove everything. I'm not proving the mean value theorem yet. I'm just using it. Yeah, I'm going to show you the picture that the book shows. Okay. So here you go again. This is the graph. It's this arc or arch in here, okay? And from -1 all the way to 4, this is the secant. That's the secant line, okay? Great. Now, you can see that the tangent here is going to be that. At this point in here, the tangent is going to be like that. At this point in here, the tangent is going to be like that. At this point in here, the tangent is going to be like that. At some point, this tangent here, this is going to be the tangent. And you can see that this tangent is parallel to the tangent of the secant here. Okay? So what is this point? It's 2 and 3. Right? And how did it find out? Remember that, well, you can go back in the video and you can see that, so the function, oh man. The function of x equals 5 minus 4 divided by x. I had discovered, okay, with those calculations that the x equals 2 was going to be the x where the derivative of 2 was going to be equal to 1, which is equals the slope of the secant, okay? Well, if you replace this 2 in this formula here, what do you have? You have 5 minus 4 divided by 2, 2. 5 minus 2 equals 3. So you can see that the y is 3. And that's how they know that this point in here is 2, 3. See? You got a 2 in here, and you got a 3 in here. And that's what you have to get out from this. That's what you got to learn from this exercise. Okay, here we got another thing here, f of x equals x cubed minus 3 divided by 2 times x squared. And it's asking to find out when the function is increasing in the slope, when the slope is increasing and decreasing, okay? All right, so we gotta find the critical points, okay? I'm going to differentiate, so it's going to be 3x squared minus, so here I know that's just going to be a 3x. How? Because this x squared is going to become an x, and this 2 is going to come down here, and yeah, this 2 is going to come down here, and when it's here, I'm going to simplify with the bottom 2, such that it's going to be minus 3x. Okay, so you want this to become a 0 to find what? The critical points. So you make this become a 0, you factor out the 3x, you got x minus 1 equals 0. So you got x equals 0 and x equals 1. These two are the critical points, okay? Critical points. All right. Now what is that? So you got domain here. Now you have minus infinity all the way to 0. You have 0 all the way to 1. And then you have 1 all the way to infinity. That's an ugly infinity. It's better. Okay. So let's just put minus half. I love these halves. Let's just put minus half in this formula here to find out the slope, okay? If it's minus half, it's going to be 3 divided by 4 minus 3 divided by 2. This is going to be equal to minus 3 divided by 4, okay? So I know that the slope in here is negative. Okay. If I didn't make any mistakes... Uh-oh, I think I made a mistake. Yes, I made a mistake. Okay, so minus half to the square is going to be 1/4, so you got 3/4. Now minus 3 times minus half, so it's going to be plus 3/2. Okay, and I'm going to put a 4 here, and I'm going to put a 6 here, and you can see that this equals 9/4. Okay, so m is positive here. Okay, in this interval, let's put half. Okay, so you have 3/4, and then you have minus 3/2. So this equals minus 3/4, and I know that the slope in here is going to be negative. If I'm not making any mistakes, I have to check this out. It's because I'm trying to go fast. So in here I can put 1.5, so which is 3/2. So this is going to be 3/2, guys, is 1.5. Yeah, 3/2 is 1.5. Okay, so 3 divided by 2, so it's not going to be 27 over 4. Okay. Minus 9 over 2. I think it's right. So 3 divided by 2, 9 divided by 4 times 3, 27, minus, and what do you have in here? Minus 3 times 3 divided by, okay, I think it's right. So I'm going to put a 4 here. Okay, and in here I'm going to put an 18. I'm just getting the minimum common denominator. And then I have 27 minus 18, which is 9/4. So in here becomes positive, if I'm not making any mistakes. So I would say, I have no idea, okay, but I would say that the graph is kind of like this. It's positive, and then, well, no, hold on. It's positive, and then the slope becomes negative in here, and then it comes over here and becomes positive again. That's what I think this thing is, okay? Something like that. And it is, okay? So you got a positive, negative, positive, positive, negative, but yeah, I did not make any mistakes. Look at this graph. I'm going to put it in here on top of everything. And now, this is the real graph. Look at that. It's not the same, okay? This one here was more, has a smaller section here. Has a smaller section here than this one. This one is larger. But hey, it's kind of the same, okay? You got a positive slope in here, and then it becomes negative, starts going down, then it becomes positive again. Okay? And are the places, the critical places, the same? Yes, because I said here that the critical place was going to be 0 and 1. So you got a critical place here at x equals 0, and you got another critical place here at x equals 1. Now, if you want to find out where the y comes from, all you got to do is replace it in the formula. You put x equals 0 in this formula here, and you're going to find a 0. If you get this one and you plug it in this formula here, you're going to find a minus half. Okay, So that's how the author of the book knows exactly where these points are. I know this is a long video, but you know, these videos are just gonna become longer and longer, guys. I'm just gonna keep going because, well, this is a calculus course, so why not? And you know, practice makes perfect, so yeah. Well, let's find, it's trying to find out when this function right here is going up and when it's going down, right? Because this is a sine, and you know, the sine is going to be like this, and it's going to go up and down, up and down, up and down forever. So, okay. X. So you want this. To be 0. That means you want the cosine of x to be half. When's the cosine of x going to be half? Well, the first time the cosine of x becomes half is when x equals pi divided by 3. Okay? And then you gotta add 60 degrees plus 30 plus 30. Okay. There's a pattern. It's just that it takes for me some time to get this pattern. Let me think here. Plus 60 and you got a minus 60, so it's 120. You have to add 240 degrees. Now 240, okay, equals pi times something. What I'm saying is that the x has to be pi divided by 2, which is 60, all right? But it has to be also this 2 pi minus pi divided by 3, which is 60. But minus 60 is also half. The cosine of minus 60 is also half. So it's going to be 2 pi minus pi divided by 3. Okay, and then you got to put a 3 here. And you put a 6 here. So it becomes 5 pi divided by 3. 5 pi divided by 3. Okay, so between, okay, 0 and 2 pi, within this interval, only these 2 points here are going to be the critical ones. All right, so you're going to have a function kind of like this, because it's a cosine thing, so it never goes away. Let me see here. Let me see if the book shows something. No, it doesn't. Okay. But it's trying to find out when it's increasing, when it's decreasing. Okay, so you're gonna have to get between, what are the domains in here? The domains is gonna be from 0 all the way to pi divided by 3. That's going to be one domain. Okay, another domain is going to be from pi divided by 3 all the way to 5 pi divided by 3. And the third domain is from 5 pi divided by 3 all the way to 2 pi. All right. Well, let's think here. Cosine of 0 is 1. And then the cosine is going down, 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 all the way until it reaches half, right? Because this is the formula here. So let's say, for example, I'm gonna erase some of the stuff in here. Now that we know, okay. Let me think. You gotta find out when the slope is negative, okay? So put like from 0 to pi divided by 3, put pi divided by, because we can't just put any value here because I don't know the values of everything, but you see cosine of 0 is 1 and cosine of 60 is half. So between 1 and half is just going down, but it's greater than half, okay, because the cosine is becoming smaller. So between this, I know that the value of the cosine in this interval here is going to be greater than half. So what do you have? You have half minus a number that's greater than half. So in the end, okay, a number, and this number is greater than half. So in the end, this is going to be a negative result. Because you have something greater than half minus half minus a larger number. So in this point here, the slope is going to be negative. Okay. Okay. Now, in this domain in here, you know that what's going to be the slope is going to be half, and you got a minus. And the cosine of everything after pi divided by 3, but before 5 pi divided by 3. So what do you have in here? You have something that's smaller than half. Okay? So it's going to be minus a number that's actually smaller than half. So this is going to come out to a positive number. So I know that the slope in here is positive. That's what the exercise is asking for, okay? It's asking when is the graph, this graph here, gonna start going up and going down and going up and going down. So in here, the graph is going down. And then it reaches this and it starts going up, okay? And then it'll come over here and I think it'll go down because it's a periodic function, but we have to make sure. So let's see. From 5 pi divided by 3, I know that the thing's going from, because guys, it's kind of complicated. This comes to trigonometry. All right. So you see at this point here, which is 0 or 2 pi, cosine is 1. Okay. And it kind of like here, the cosine is going to be half, and the cosine is going to be half in here too. So this domain in here, okay, is this way, all the way up to 2 pi, up to here, okay? Now at this point, it's become, what are you going to have? You're going to have half in here minus a number that is either greater than half or smaller than half. Oh, it's greater. Here it's half, and here it's going greater and greater and greater and greater until it becomes 1, okay? So I know that the outcome of this stuff is going to be a negative number, and m is less than that. So you can see that this is going to be the graph, okay? What is at this point here? Well, at this point, x equals pi divided by 3, and at this point here, x equals 5 pi divided by 3, okay? So this is going to be the first domain, the second domain, and the third domain. So the first domain is this one. This is the first domain. The second domain is this one. This is the second. The third domain is this one, all the way up to here. This is the third domain. I'm erasing, okay? I'm going to give you guys some time to pause the video. And I think I'm just going to do one more exercise because I've been in here for some time. Let me think. Actually, the book shows the the thing here, the graph. So you see, what did I say? That the first domain was going to start in pi divided by 3. Well, look at this. Okay, here you have pi, and this pi, this is pi, right? And it's being divided into 3 sections, 1, 2, 3. Well, right here at pi divided by 3, what do you have? Okay, right here, what do you have? You have a tangent that's 0, that's horizontal. Oh man. And here you have 5 pi divided by 3, remember? And here you got another tangent that's horizontal. So that's it. That's what the thing was asking. And remember I said m was going to be negative here, and here m was going to be positive, and here m was going to be negative. And there you go. That's what the exercise was asking for. And that's it. Guys, I think that's enough. Or maybe not. I'm gonna keep going with this as long as it's just the exercises, because when we have to enter a new topic, then I'm gonna go to the next video. But as long as we're in the same topic, just making exercises to fixate this in your memory, okay, just to practice, I'm gonna stay here. So let's find it's asking us to find the critical points of this function. Let's do this. It's going to be 2/3, taking the derivative, okay, it's going to be 2/3 x squared minus 4 to the minus 1/3, because it's 2/3 minus 1, you got this, times the derivative of the inner function, okay? So this is going to be 4x, all right, divided by 3, got this, the cubic root of x squared minus 4. All right, so here's an interesting example, because I said that the critical points was when the tangent exists and then it's 0, or when the tangent doesn't exist, okay? Which means that the tangent, as it gets close to a point that doesn't exist, it's going infinitely large or it's going infinitely small, okay? So it's approaching infinity to the positive or negative side. So thinking about this formula here, okay, when is this going to be 0? This is going to be 0 when this x in here is 0, because then you're going to have a 0 divided by 0 squared, 0, and then you have a cubic root of minus 4, and it's okay to have a cubic root of a negative number, so it'll be something non-zero, multiplied by 3 is going to be something non-zero. So you have 0 here and whatever here, which is going to be 0. So I know that this formula here, the critical points, the x critical, okay, they're going to be a 0, and they're also going to be at minus 2 and 2. How do I know that? Because if you put a minus 2 here, minus 2 squared, 4 minus 4 is 0, and then you have the cubic root of 0, which is 0, times 3, 0. Okay, so if you put a negative 2 in here, you're going to have negative 8 divided by 0. If you put a 2, you're going to have a positive 8 divided by 0. So this can never happen, but as x approaches something, as the denominator, as x approaches 2 and minus 2, either from the right or from the left, okay, these things in here are going to approach 0. So I know that this stuff in here is going to approach infinity, it's going to approach negative infinity, and this one here is going to approach infinity. All right. So the domains, let's worry about the domains now. Let me see here. The domains is going to be minus infinity. I wish I could do a perfect infinity. Minus infinity to minus 2, right? And then you have a minus 2 all the way to 0. You got from 0 all the way to 2. And you got from 2 all the way to infinity. All right. And now if you want to find out the m for each one of these domains, if they're positive or negative, just plug values between these domains in x in here and x in here, and you get it. Okay, let me see here if the thing okay, see, yeah, all right, let me show you the graph. There's the graph. See, now from negative infinity to minus 2, you see here you got as x equals 0, x equals minus 1, x equals minus 2. What did I say? If you plugged in, I didn't plug in this time because I don't want to waste too much time with this, but if you plugged it in, you were going to find that this formula here becomes negative, right? For all the values. And it approaches negative infinity. Okay, you can see that the tangent's doing like this. So it's approaching negative infinity in here. That's a critical point. Okay. In this is the second domain. Coming over here, you can see that it starts from positive infinity and it approaches 0 here. Here it goes in the third domain from 0 all the way to negative infinity, and this one starts at positive infinity and goes all the way up. Okay, these things in here, this point and this point, these are called cusps. Okay, so you have something like that. Here you go. These cusps, you can see that the limit doesn't exist in here because approaching from the left, you got negative. Approaching from the right, you got positive. In here, it's the opposite. Approaching from the left, you got negative. Well, it's the same thing actually. And going from the right, you got positive in here. So the limit doesn't exist. The limit partially exists. Okay, it exists for. Let me see again. The limit exists completely for this domain because this is excluding the minus 2 because of this parenthesis here. So it's excluding the minus 2. At minus 2 itself, you don't have anything. And then you're going to think, okay, but this function, is it defined everywhere? It's defined everywhere, okay? I mean, if you put a negative 2, I just want to show you guys this thing here. If you put a negative 2, it's going to be, oh no, actually it's not defined. No, that's right. It's not defined. Because if you put a negative 2, it's going to be minus 8 divided by 0, which doesn't exist. Okay, so you see these points in here. Okay, this point in here and this point in here, they should not be filled. This is wrong. Okay, there's supposed to be empty circles like that because the function is not defined in here. If you put a minus 2, this is what you get. This is what you get. This doesn't exist. Okay, and if you put a 2, this is what you get. So it doesn't exist either. So this graph is kind of wrong. Let me think. Guys, you know what? I think you guys are getting tired, and me too. So I'm gonna, I don't know if I'm just this once more. The function is x to the 4th plus 1 divided by x squared. In order to find the extreme values, or maybe not the extreme values, but the critical points, you gotta find the derivative of the function that either doesn't exist or that it has a value of 0. Okay, you can see that I'm gonna have to use the division here because you gotta do this one times the derivative of that minus this one times the derivative of that divided by the square of this one, right? Remember, it's the differentiation division rule, but instead of doing that, I'm just going to divide the whole thing. Okay, so this equals x squared plus 1 divided by x squared, or plus x to the minus 2. Yeah, now differentiate it. So 2x, and then it's going to be minus 2x cubed. Minus 2x to the minus 3. Okay, so this equals 2x. I'm going crazy here. Minus 2 divided by x cubed. This is the formula, right? And you're gonna find out when this is 0. So, well, okay. Gotta find out when this is 0. So I'm just gonna put x cubed in here, and I gotta multiply this thing to x cubed, so it's x to the 4th. Okay. Cross multiplying, you have 2x to the 4th minus 2 equals 0. You divide everything by 2, so x to the 4th minus 1 equals 0. X to the 4th equals 1. And then you have x equals the 4th. How can I say this? The 4th root, or yeah, the cubic root, the 4th root. Yeah, or it could be the root to the 4th power. Yeah. Root to the 4th power is going to be like that. I'm trying to find the right terminology. I think it's, yeah, the 4th root. It's going to be the 4th root of 1, which equals plus or minus 1. So plus or minus 1 are going to be the critical points, okay? So you have the domains in here. The domains are going to be negative infinity all the way to minus 1. And from minus 1, yeah, minus 1 all the way to 1, if I'm not making a mistake. Yeah, 0 this time is not a critical point. And from 1 all the way to infinity. Okay. Now, if you plug these values in here, let's try to do this one more time. Let's put minus 2. It's going to be minus 4 minus 2 plus 2 divided by, this is a minus 2. Okay, because minus 2 cubed is minus 8, but with this minus, we got a plus, and we got an 8 here. So this equals minus 4, okay, plus 1/4, and minus 4 is greater, so this is negative. Let's see if I can do this kind of fast in here, but without making any mistakes. Let's put a, you can't put a 0. Can't put a 0. Let's put half, yeah. Because it's going to be a value within here. So I'm going to put half. It's going to be 1 minus 2, okay? And half in here is going to be 1/8. Multiplying, got an 8 here. Okay, 1/2. Hold on. Yeah, half in here is going to be 1 minus 2 divided by 1/8. So you got that, which is minus 15. So I'd say that it's also negative here. And then you have, I'm just going to plug in 2. Plugging in 2, you got a 4 minus 2 divided by 8, which is minus 1/4. So m in here is going to be positive. Let's see. But you got another one that I forgot. Yeah, you have these, but you have another one. which is the one when it doesn't exist. I'm sorry guys, I made a mistake. You have all these three domains which are right, okay, from minus 1 all the way to 0. Yeah, it's not, what did I put in here? I put half is gonna be, yeah, this is right, but it's not, you gotta do minus 1. From minus 1, you gotta put all the way to 0, and this is gonna be from 0 to 1. So I'm gonna have to erase this, because in here I use half. So this is gonna be from 0 to 1, okay. And then you got another domain, which is from minus 1 all the way to 0. Why? Why is 0 part? I thought it wasn't a part, but it is, because I forgot that you gotta find the critical values are for when the first derivative is 0 or when it doesn't exist. Now when it doesn't exist, when this numerator here is 0, okay, so if you put a 0 here in this formula, what are you gonna have? 2 times 0, 0, minus 2 divided by 0 cubed, which is 0. So you have minus 2 divided by 0, which doesn't exist. So 0 is also a critical point, okay? And when you put minus half, I'm going to plug in minus half in here now. So it's going to be minus 1. Since it's a minus half cubed, it'll continue being a negative number. With this negative, is going to become a positive number. Okay, so plus 2 divided by, this is going to be 1 divided by 8, oh, coming over here is going to be 16, okay, so this equals 15, so m here is positive. I'm going to organize these things. I'm going to put them a little bit here, and this one, I'm going to put it here. Okay, everything else kind of doesn't matter now. Alright, now I'm going to show you guys the thing in here. Maybe increase this a little bit like that, just so it's clear. All right, so you see, from negative to minus 1, the slope is negative. There you go, the slope is negative here. From from minus 1 all the way to 0, the slope is positive, and I got it right, it's positive here. From 0 all the way to 1, the slope is negative. From 0 all the way to 1, the slope is negative, I got it right. And from 1 all the way to infinity, the slope is positive. From 1 all the way to infinity, the slope is positive, I got it right. So there you go. That's what the graph looks like. Okay. Whenever you have how can I say it? Whenever you have a graph whose first derivative, the first differentiation part, yeah, the first derivative of the function approaches positive infinity or negative infinity, like here, this part and this part, what you got in here is an asymptote. You guys remember that? It's something that goes like this. It can never be 0, okay? So this thing here is going to approach 0 like this, but it's never going to be 0, and so will this one. It's always going to approach 0, x equals 0 like this, but it will never be 0. In the end, what you have is a graph like that. Okay, you got a graph in here, and you have this thing, which is going to approach 0, it comes here, and it'll approach 0, approach 0, approach 0, approach 0, approach. It's also going to approach infinity, see? And the other one comes approaching from negative infinity, approaching. And then it comes all the way down here, and it approaches infinity and goes. All right? But the graph actually goes this way. The graph is going to go, the x is going to increase this way forever, and it's going to increase this way forever, but not in here. At 0, it never crosses. The graph never does this, okay? The graph approaches, and then approaches down, and it goes. So that's the 0 here, the y-axis is an asymptote, right? The y-axis over here. This is an asymptote of this graph. Okay, that's it. On the next video, we're going to talk about concavity tests. So that's really something for the next one. Okay, guys, this is it.